All right, howdy y'all. So we have one more lemma before we can take on the interpolation theorem. In Folland, it's 6.26. It's called the 3 lines lemma, and it has to do with the log concavity of vertical lines on holomorphic functions on the unit strip, where the real part is between 0 and 1 in the complex plane. So we're going to have a function phi bounded and continuous on the real strip, or on the strip in the complex plane with real part between 0 and 1, and we want to be holomorphic on the interior. Then, if we have a bound on the function for when z has real part 0, and a possibly different bound for when z has a real part 1, then we get that in general it will have a bound for any real part t within the interval, where the bound is given by the transition from m0 to m1 in this kind of the standard logarithmic way, where you have 1 minus t and t. So it's a transition from that bound to that bound. So what we're proving is log concavity horizontal to the complex axis. So, horizontal to the complex axis. We're showing log concavity of any holomorphic function that's continuous on the strip with the bounding conditions. So what we're going to do, and this is not in Folland, it took me forever to figure out, I had to look all over the internet to figure out why he was able to just do this, but we're allowed to assume that m0 and m1 are both equal to 1. And the reason that we can do this is that we can normalize phi of z in this way by creating a new function, phi of z, that's phi of z over this product. So we take our bounds, take 1 minus z and z as the power, so we use the same sort of transitional thing, and we use that to normalize the function on the bounds. Because now when z has a real part 1, we're going to be getting that bound, and at least in magnitude, and we're going to be getting that bound when z is 1. So that's why you're allowed to do this normalization here. Now, when we have epsilon, for all epsilon greater than 0, we can define theta sub epsilon of z, where we take theta sub z and then multiply it by e to the epsilon theta z squared minus z. And then, because this still meets the hypotheses of our lemma for all epsilon, we now get to play around with the properties of it by taking the limit as the imaginary part of z goes off to infinity, which we know becomes 0. And the reason that it becomes 0 is that when you square a complex number, the real part becomes arbitrarily large in magnitude as the imaginary part becomes arbitrarily large. And the reason for this, because the real part is between 0 and 1, so when we square it, the complex part we don't care about, but the real part is going to, that's produced by the product of the two real terms, is going to be staying between 0 and 1, and the product of the complex part, because it has an I, is going to become arbitrarily negative. So arbitrarily large, but negative. And when you raise e to a large negative power, this thing drops off to 0. So now, what we have is that this thing is theta sub e of zeta is less than or equal to 1 on the boundary of the rectangle that's bounded by our strip, and by, in the imaginary direction, by negative a and a, where a is taken to be some arbitrarily large number that is large enough for this condition to be held, because again we have that this limit is going to 0. So we can ensure that it eventually gets less than 1 by picking a sufficiently large a. Now, because we have a compact domain, or a compact domain of the function where it has this property on the boundary, we know that it must not have any local maximum within inside of the thing, because we know what the boundary looks like. So we know that it can't have any local maxima greater than 1. So using the maximum modus principle, we get that it in fact is less than or equal to 1 inside of the inside of this entire rectangle for all a. And then, because A was chosen arbitrarily, and we can make it arbitrarily large, this shows that it's true for the entire strip. Now that we have that it's true for the entire strip, what we get is that theta is equal to the limit as epsilon goes to 0 of in magnitude is the limit as epsilon goes to 0 of theta epsilon z, which we now know is less than or equal to 1. So what we get here is that theta is in fact also less than or equal to 1. And because theta is less than or equal to 1, we can take our definition of theta and divide over by the bounding conditions here, and we get, because it's in magnitude, we have our z's here. But we're taking the magnitude, so we only care about the real part because the complex part is just going to give us a direction. So then we get that these are t, which is what we were trying to prove for the real part of z being, and which gives us the result as desired. So therefore, okay. In the next video, we're going to get started on the interpolation theorem. It's going to be broken up into several videos. It's long, so bear with me. Anyway, I'll see you guys in a bit.